right, so we'll do a few more harder examples, boys, and see how we're going. All right, so we're finding the area of each shape to the nearest square metre. So let's look at the first one. Now, I've divided this up into two sections, area 1 and area 2. So area 1 I've picked with the curved part because it's always going to be a bit trickier. So we're doing that part first. So area 1 is a quarter of a circle. I can see that because that's a right angle. Okay, so a right angle is 90 degrees over 360 degrees. And if you put that in your fraction key, it's a quarter. All right, or if you just look at a pie and you cut out a piece with a right angle in it, it will be a quarter of the pie. So it's a quarter of pi r squared. The radius is this or this, but that part is coming from here. So if we just go over there, that will be a 12, that section there. And that's what we're using for our radius. So it's a quarter times pi times 12 squared, we'll get that answer. Then for area 2, we're dealing with a rectangle. So it's length by breadth. So it's 15 by 12, which is 180. So we need to total those two areas together. We total the areas together and we get that answer. And now we're going to the nearest square metre. Now, nearest square metre means the nearest whole number of square metres. So we're going to draw our line for rounding after the whole number. That's less than 5, so that's going to stay as a 3. So 293 metres squared. Now this next one, this is actually called, this shaded area is called an annulus. And an annulus just means that you have two circles, they're called concentric circles. Concentric circles share the same centre. So that centre is the centre of the small circle, but that centre is also the centre of the big circle. So we have concentric circles, and the area between them is called the annulus. So we're finding the area of that annulus. So I'm going to put this all in one formula. I hope you can cope with it. We're doing pi r squared of the big circle minus pi r squared of the little circle. So what's actually happening here is we have the big circle. I'm going to find all that area. Then we're going to cut out the circle area in the middle and remove it and throw it away. And that will leave us with this piece we want. Okay, so we're going to do pi r squared for the big circle minus pi r squared for the little circle, and that'll give us our answer. So our radius for our big circle is 14. So we're going to do pi times 14 squared minus the radius of the little circle is 6. So minus pi times 6 squared. And then just work it out and round off to your nearest whole number. That's a 5 or more, so this goes up by 1. Okay, so looking at the next question, and we're getting into more interesting questions now. So the diameter of the Earth is 12,756 kilometres. Really, Earth's not as big as you think it is, but I suppose that's a fairly big diameter. We're looking for the circumference of the Earth. So if you went all the way around the biggest part of the Earth, how far would you be going? So we're finding the circumference. I'm going to use pi d because they did give us the diameter. So it's pi times 12,756 kilometres gives you, once we round it off to the nearest whole number, because they've asked for that here, 40,074 kilometres to go all the way around. So for instance, the equator. If you went all the way around the equator, that's how far it would be. Now the International Space Station, I'm sure, well I hope that you know that we do have an International Space Station, and it sits up above the Earth. They do a lot of research up there, and people are employed in that International Space Station. So you might one day want a job there. All right, so you would fly up and be space stationed up there, have everything there that you need. And that space station is orbiting the Earth. Okay, I'll just go and get my shapes here. So this is the planets. Okay, we have the sun in the middle here, and these are the planets going around the Earth. All right, so I'm going to look here at Mercury. Mercury is this little small one. Oops. So the International Space Station is a little bit like this. All right, so you can see it's a little bit off the surface of the Earth and it's rotating around. And we have satellites and things that do this as well. Right, so there's a lot of satellites up there. That's how we get our television and stuff from the United States or from Europe. It actually sends a signal from one part of Earth, on Earth to a satellite, which then beams it straight down to another country on Earth. So it goes via satellite. All right, so this is something like the International Space Station orbiting the Earth. Okay, so what we're telling you here is that its average height is 400 kilometres above the surface of the Earth. So if you can see here, if this is the Earth, it's not, it's the Sun, but pretend that's Earth, and this is the distance we're talking about, 400 kilometres between the International Space Station and the surface of the Earth. Okay, so if we look at this and draw a diagram of it, because we've got to find the distance that travels in one orbit. So here we are, we've got the Earth, it's circular, it's a sphere but it's circular. It's got a diameter of 12,756 kilometres and the International Space Station is here. International Space Station. Okay, so that's where it is. It's revolving around the Earth like that. Okay, so we're now going to find this, how far it travels. We need to find the circumference of that red circle. So to do that, we're going to do 2 pi r. Now we need to find the radius of the red circle. So we need to go from here to here to find the radius that we need. So to do that, we're going to get the 12,756 divided by 2, right, because that'll give you this bit. That's what that is. And if you work that out on your calculator, let's see if I can do this in my head. You get that, and then you're going to add on the 400. Right, so we're going to do that, then we're going to plus the 400, and that will be 6,778 for our radius. Then if you calculate 2 times pi times that, you'll end up with 42,587 or so it doesn't actually ask for any rounding here, kilometres. And you would expect that that would be bigger than this, which it is. All right, because it's further away, it's going around a bigger circle. Okay, number 6. We're looking at a square courtyard. It tells you it measures 5 metres by 5 metres, and it's going to have semicircular areas attached to each side. Okay, so let's have a look at this. I think I might have done this wrong, so we better start by a diagram because I was trying to do this without a diagram and I've made a mistake, but we'll fix it up as we're going. All right, so we have a square. We know that a square has 4 equal sides and right angles, and we're going to add a semicircle to each side. So it's going to look like this. Okay, that's what the whole thing's going to look like. So I'm going to find the area of one square. Now I should have found the area of two circles, because if I put these 2 semicircles together, that will give me one circle. If I put these 2 semicircles together, that will give me 2 circles altogether. So I should be finding 2 circle areas, not one circle area like I've done. So let's just fix this up. It should be 2 times pi r squared, because we have 2 circles altogether. Now, to find your radius, if we have a look at it, the radius of the circle, now this bit here is 5 metres, the black bit. So we want to get half of that from here to here. So the radius is going to be 5 divided by 2, which is 2.5. So that's what I'm going to put in here, 2.5 squared. Now when I go to the calculator, I'm going to get something different to this. So let's have a look at what we've got. So if I go to my calculator, I am putting in 2 times pi times 2.5 squared. Okay? And we end up with this answer here. And we have to give it to the nearest square metre, which will be 39 square metres, rounding to the nearest whole number. So 39 is what we end up with there. Okay, now the next question says, by what percentage has the area of the courtyard increased? Well, I've mucked this up, so I'm just going to fix it. Okay, so when we do this, we're looking at the increase in the area. So that has to go on the top. That's the important thing. Always on the bottom will be the original, unless they tell you some other special thing. But it's always on the original area. So the increase in the area is what they're talking about over the original area on the bottom. And then we want to make it a percentage, so that tells you to times by 100. So that's what I've done over there. Now, the increase in the area are all these semicircular bits we've added to it. So we've worked that out, and it's 39. That's your increase in the area, all the extra semicircles you put on. The original area was just the square, so it's 5 times 5, length times breadth, or 5 squared if you're going to do it with your area of the square formula. So if we put this in, it's 39 over 25 times 100, and we'll just work out what that is on your calculator. And we get 156. So it's actually increased the area by a lot, adding those 4 semicircles to the area of the courtyard. All right, now we're going to do one more question here. I was going to leave this one out, but I think there's going to be a few of you have problems if I don't do it. So I am doing one. So let's have a look. It's number 7, and we're looking at what happens when the wheels of any vehicle are turning. All right, and this question says we have the wheels of a bike. They have a diameter of 66 centimetres. That's a lot of bikes do have a diameter of about that on the wheels. How far will the bike move after one rotation of the wheel? All right, so what happens with this is you have a wheel. There's your wheel. Let's consider that to be one of the spokes on your wheel. Now, as that travels, right, as that point there goes all the way around, it's like we are unravelling the circumference, right? So all of this bit here, this whole thing ends up unravelling like that. Okay, so we are looking at the circumference of a circle here, and when it unravels, it looks like that. Okay, so it's really, when the bike starts, the spoke is here, by the time it gets back to there, it's gone through that much distance. So one circumference actually tells you how far you will travel on the road. Okay, so if you've got a bigger bike wheel, one rotation will take you a lot further. Okay, so we're going to do c equals pi d because we do have a diameter here. So it's pi times 66, and that's the answer we get. So one rotation of the wheel will go 207.345, whatever, they haven't asked for rounding, centimetres. Okay, so just over 2 metres it's going to travel with one rotation. All right, now in part 2, how many rotations of the wheel are needed to cover a distance of 5 kilometres? Now watch the units on this one. So for the rotations, we're going to do 5 kilometres and divide by just how far it went in one rotation. So we want to find how many rotations. We've got to do the distance we need, 5 kilometres, divide by how far you go with one rotation, which is 207 roughly centimetres. I have to make sure these units are the same. So I've decided you can do it in both kilometres or both centimetres, but I've decided to take them both to metres. Okay, so this one here, to go from kilometres to metres, I have to times by 1,000. All right, so 5 times 1,000 is 5,000 metres for the top. On the bottom, I'm taking centimetres to metres. So I'm going to a bigger unit, so I'm dividing by 100, because there's 100 centimetres in a metre. And if I do that, I'm going to get that answer. Now, because they're both in metres, I can now do the division. And the calculator will then give you 2,411 point whatever rotations. Okay, so I hope you understand that concept of what your wheel is actually doing. Okay, so that's the end of the lesson. You're going to try some of these for homework.